Newton's universal law of gravitation is an equation and an idea that tells us that all objects, regardless of how far apart they are, exert a gravitational force on one another. So for example, this object, mass m, lowercase m here, and mass capital M here, exert a gravitational force on each other, and that varies with this distance apart that they are. And one very important thing here is notice that this distance that we're measuring, r, is between the centers of mass, not the surfaces of, let's call them planets for now. Okay. So what Newton's law really does that makes it so important is actually allows us to calculate what is the gravitational force between these objects. And his universal law of gravitation looks like this, where we have Fg equals g, lowercase m, capital M for our two different objects, over r squared, so the distance between them. So g mm over r squared, this g is our Newton's universal gravitation constant, which is just equal to 6.673 times 10 to the negative 11th Newton meters squared per kilogram squared. So anytime you see this capital G, when you're working a problem, you're just plugging this number in here. It's a proportionality constant. M, lowercase m, the mass of one object, capital M, the mass of the other. Usually it's the smaller mass, the bigger mass, but it really doesn't matter. And then over r squared, so distance squared. So kind of one important thing to know is that if we were to think about making a graph of our force of gravity versus the distance things are apart, because this is proportional to 1 over r squared and not just 1 over r, our graph looks something like that, where it's going to fall off very, very quickly as we go. That's why you don't necessarily feel the force of gravity between you and something that's very, very far from you, because that force is just so incredibly small. And because this number g is so small, right, 10 to the negative 11th, unless you have a really big mass here, like mass of a planet, to make up for that small number, you really don't notice the effects of gravity, right? For example, you don't notice the effect of gravity between yourself and the pencil sitting on your desk, even though technically it exists. That's because it's so incredibly small, you just don't notice it. We can also use our universal gravitation to figure out what the acceleration is of gravity near the surface of an Earth, right? Forces are equal to mass times acceleration per Newton's second law, and then that force, if it's gravity, would be g m over r squared. Well, masses would cancel out, and I'd get acceleration equals g, and in this case maybe mass of the Earth, radius of the Earth squared, and that would give me an acceleration near the surface of whatever planet, in this case the Earth. If I actually plugged in the values for Earth here, then I would get our usual 9.80 meters per second squared. And that's part of the reason we know that that number is accurate, and then verify it via experimental results. Tides are another good example of that 1 over r squared relationship. So remembering that Fg is proportional, not equal to, proportional to 1 over r squared. So it's going to change fairly quickly with changes in distance. With tides, right, the moon is going to exert a gravitational force on the Earth, just like the Earth exerts a gravitational force on the moon. Equal forces via Newton's third law. So because this point on the Earth is closer, so let's call that maybe R1, is closer than the center of mass of the Earth right there, R2, there's going to be a greater gravitational force here on this side of the Earth than there is on the very center of the Earth, which means it's going to get pulled harder towards the moon, and that, because a liquid can move a little bit, is actually going to pull it a little bit off of the surface of the Earth, and that's where we get a high tide on this side. The harder one to think about is high tide on the opposite end of the Earth. Right, and there exists a high tide there. Right, in a 24-hour period, you get 2 high tides and 2 low tides. The other one comes when you're on the side of the Earth that is exactly opposite of the moon's location. And that is because R2 here, the center of the Earth, is being pulled harder by the moon than this far side of the Earth where there's water. And because the Earth is kind of surrounded by this fluid, it can kind of pull it this way. And so the Earth itself actually gets pulled by the moon harder than this side of the ocean does, if you will. And so that actually sort of pulls the Earth away from it, leaving a kind of gap here that results in high tide. Weightlessness is another important thing to think of here. In this case, the important thing we want to illustrate is that weightlessness does not mean no gravity. Okay, we have a tendency to think that a little bit, but it's definitely not the case. If we take the Earth here, and we take something in orbit around the Earth, so something's moving, say, this direction around the Earth. Let's call it the space station so that there's people on it. We see those people floating around, so it looks like there's no gravity there. In actuality, there is gravity there, right? They have mass, the Earth has mass, so they're being pulled together by Newton's Universal Law of Gravitation. We could actually calculate what that force would be. So picture putting an object into orbit. Let's imagine, maybe we're shooting this object out of a cannon and shooting it around, right? If we shoot it far enough, we get our normal projectile motion. If we shoot it fast enough, we end up on our path like this, where we sort of fall like that. And our path, that projectile path, actually sort of has the same shape as the curve of the Earth. And that's kind of what's happening when an object is orbiting, that it's just on that path. Now, it's in a state of free fall. So that means that that object has an acceleration that is equal to g at that point in space. Now, g is going to vary a little bit, especially being far from the Earth. It's going to be less than 9.8 because of that distance. But there is still that gravity there pulling it down, but it's pulling down both the spacecraft, so there's our box, there's our spacecraft, and the person inside it, our astronaut, are both accelerating towards the center, so in this case a centripetal acceleration, with g. And so because they're both falling at the same rate, it's as if he can't sense, as the astronaut, moving towards one wall or the other at a faster rate, because they're all falling at the same rate. So weightlessness is just actually a form of free fall. It doesn't actually mean that there's no gravity there. You may be asking yourself at this point, well, how do we know that g has that particular value anyway? How would we figure out such a thing? 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. This was kind of the experiment that helped us prove that, and helped us prove that there was gravity between even two small masses, things that are harder to observe. So what we did is we had a little pivot here, and this was Cavendish who designed this experiment. And we have this bar with two larger masses on the end of it. And then we have a fiber here that's allowed to rotate, and it's attached to this bar with two smaller masses on it. And then we have a light source hitting a mirror, usually a laser hitting a mirror, and goes to a scale over here. And what's going to happen is, over time, this mass is going to be gravitationally attracted to the other one, or they'll be gravitationally attracted to each other, would be a better way to put it. And this is attracted to this one. And so it's going to cause that fiber to rotate and pivot, and as it turns, our laser is going to mark different points on the scale as it's turning. And so we can kind of see, well, how quickly is gravity causing it to turn? And thinking about our equations with force, we could pretty easily come up with our constant by just graphing some of our data. And so this was how they can actually verify this, and that they saw that even these two masses, things we wouldn't normally expect in everyday life to just, maybe roll towards each other, by setting up the right conditions and eliminating a lot of frictional sources, are actually attracted to each other, as Newton's universal gravitation suggested they would be.